Okay, so today we're going to talk about disinfectants. I'll take about half the time. I got a Kahoot for you, so a little fun trying to put those back in where I can anyway. And then we're going to talk about antibiotics, which is my favorite topic. Actually, they're all my favorite topic. But it's something near and dear to my heart for a few reasons, which maybe we'll talk about that a little bit later. Okay. So this is first half of topic 9, where we were talking about physical methods of control, and it's not an all-exhaustive list. If you're an engineer, then you're probably thinking about other things, for example, positive pressure and negative pressure and things like that. And I don't know if you're aware of what that is. For example, in certain rooms, the pressure is either pushing the air out or sucking the air in, and that's another way that microbes can be controlled. Again, that's something that's a little bit more structural and is thought about when a building is designed. It's really hard to do retrospectively. So there's a lot of things can be done, and like I said, a lot of these things it's kind of almost a newer concept in the last 10, maybe 20 years, where we're thinking a lot more about built spaces and in terms of what is going on. I was at a conference a few years ago, and they were talking about building a new hospital somewhere. And of course, the new hospital does not have any microorganisms, or at least pathogens naturally. And so they actually did a huge study to watch this hospital, in a sense, get colonized by various microorganisms as patients and whatnot were put in there, and as procedures went on, and they had all these recommendations for future builds. And so this is something that's kind of interesting too, but kind of related to this. So today we're going to talk about disinfectants. So a lot of these are chemicals, and I know people have different levels of comfort with chemistry, and I have a lot of chemical structures. You don't need to know the chemical structures. I like chemical structures. They're there for me. Past life, I was a chemist, so something else to think about. Now, a lot of these things, though, believe it or not, you may have seen them somewhere before, which is why I'm going to show you some pretty commonly used household products and things like that kind of fall into these categories. Okay, so I know it's a long list, and I would say, when you're studying, I know it's going to be difficult to try to learn all of them. So try to learn some different ones for different applications. It's one of my recommendations. And I'll show you an exam question that I have at the end here, and what I'm going to do. I do one every year, a different scenario. And what you have to do is tell me what you're going to use to deal with this scenario. And so you don't have to have all of the answers, but one or two options are going to help you to get through that exam question. Okay, so I'll show you what that looks like at the end here. So let's get into these and talk about how these chemicals work a little bit, and kind of what and when they're used for is kind of the big question, right? The first group is phenol and phenolics. So again, this is a little bit of chemistry. This is these are the structures of these things, and if you do organic chemistry, you talk about these because there's some unique chemical properties about them. And one of the chemical properties is that they're a little bit more reactive than normal alcohols. Alcohols are things with the OH group on them. And it turns out the one on top, phenol, there is actually a very nasty chemical. I had a lab that I used to work with it in, and it's the kind of thing like if you get it on your skin, you want to wash right away because it will burn you a little bit, right? I don't think we ever had any accidents. But what I do remember working with the phenol and giving me a nasty headache. It's very, very strong chemical. And this is actually what Joseph Lister used way back in the days when the germ theory was kind of becoming a thing. And he was, if you remember, he was a surgeon. He was looking at understanding, okay, we want to sterilize and clean up the surgical room. And so they were cleaning everything with phenol. And it was super nasty, but it worked. So there's phenolics as well, which are a little less nasty in terms of they're not necessarily going to burn your skin, but they're all really effective compounds. And they basically, they will destroy all sorts of structures in cells, membranes, and proteins, like I said, relatively reactive compounds. So what are we talking about in terms of actual products? There's a whole bunch of cleaning products that fall into these categories. And the one that probably most people are familiar with, it seems to be in every kitchen, is Mr. Clean. You probably know when and it's used for cleaning up floors, right? And usually what you do when you you have Mr. Clean. I don't know what the exact formula is, but it's a bunch of water, and then you dump a little Mr. Clean in there. So you don't even have to use the chemical full on force, and it's relatively effective. You dilute it quite a bit. Like I said, I don't know how much you dilute it, but quite a bit. And the other thing you might notice is Mr. Clean kind of has an odor to it, not the chemical odor, but what's the other odor? Yeah, so they know it stinks, right? So they add the lemon to it, right? Pine Sol, I guess, I think, is that lemon smell too?
Pine tree.
Okay, yeah, I remember my mom having it. I haven't actually, I think, purchased it as an adult myself, but I remember it having a strong odor. So pine tree, sure, that's a nice smell, right? Why not, eh? There's a whole bunch of these cleaning products. This one here, triclosan, do I have a slide on that one? I'm not sure where we're at in that, but that one used to be included. You used to be able to buy these things, and they would be called antibacterial dishwashing detergent. I haven't seen that in a while, but anything that said antibacterial usually meant it had the triclosan in it. And like I said, I'm not sure where we're at in it, but in Canada, it is now banned in a lot of products. And so I don't know whether it's dishwashing detergent or where we're at. I don't know whether it's a phased-in kind of thing. You still find triclosan in certain things. If you ever buy, if anyone here is into yoga and you have a yoga mat, you may have seen that some yoga mats are antibacterial, right? So they actually embed that chemical in there to try to prevent, bacterial growth from, from your sweat, I guess, right? So it's in a lot of products, but it's kind of disappearing because of some safety concerns, and just, we're talking about people dumping loads of the environment. And the worst thing is about putting it in dishwashing detergent is that dishwashing detergent, the detergent itself, is actually antibacterial. You don't need to add extra stuff to it, right? So we'll talk about detergents in a few minutes. Okay, so group number 2 are alcohols. Oh, the other thing about these that are really good is that they're relatively persistent. And this actually makes pretty good for, like, let's say mopping a floor, right? The chemical kind of lingers for a while, and that's actually a good thing in that case. You could imagine this scenario, I think I mentioned last day, somebody vomits in a waiting room, and, having the chemical linger around kind of doing its job is kind of a good thing. The reason why I mentioned that is because the second group, alcohols, is somewhat the opposite. Alcohols do not linger. They actually evaporate very, very easily. And so alcohols are things with OH on them, but as you can see here, this has an OH, but it's because of that benzene ring, it makes it actually more reactive. And there's a whole bunch out there. Really, the 2 main ones that are used are ethanol. Ethanol is the same ethanol you'd find in alcoholic beverages, and isopropanol. And there's a whole bunch of products, but the main ones that you're probably familiar with are hand sanitizers, or the little wipes, the little alcohol wipes that might be used, before you get a needle or something, so to clean the surface of somebody's skin. And so, like I said, the good news about this is it evaporates. It's not going to stick around on your skin for too long, and you can feel that when you put hand sanitizer on. You can actually feel your hands get a little cooler, and that's the act of the chemical actually evaporating and taking a little heat from your hand in the process. Some, though, you might think it lingers, but it's not the alcohol that's lingering. It's something else. I'm trying to remember where I went. I had to go, was it a bank or somewhere with a teller. And they had this hand sanitizer. It was the stickiest, goopiest stuff I'd ever had. I was just really upset that I'd actually used it. It was terrible. And some of them have, there's additives. Some people add aloe vera and smells, and to try to make them more pleasant. But really, the active ingredient is some sort of alcohol. And the research shows that 65 to 70% is actually optimal. 100% is not as good as 65%. Go figure. I don't know if there's a mechanism behind that. I actually haven't looked that one up. But like I said, there's tons and tons of products. So just a second here. I'm just going to come back to that in a second. I found a picture of one. I guess I forgot to include. I was going to show you. I found a hand sanitizer somewhere, and it said alcohol-free. And it's like, well, that's great, but alcohol is the active ingredient, right? So if you ever buy hand sanitizer that's alcohol-free, it's worth it to Google what the active ingredients are. There are a few out there that are effective, that are alcohol-free, but they're not as effective as alcohol. And then there's a few out there that are just scams, right? It's one of these things trying to be all natural or something like that, right? And of course, like, well, alcohol is natural. Believe it or not, Labatt's, right, a beer company, right, they make hand sanitizer. It's the same process. You've got yeast, it's eating some natural food, and it's making this chemical called ethanol, right? And they scaled that up during the pandemic, apparently. And they're making a killing. So here's the question, right? What was I going to say about this one here? Oh, I guess I already said this. I kind of want to just talk a little bit about, okay, all right, hand sanitizer, soap. Okay, and there's actually been a ton of studies done on these, right? So this one here is saying, you know, soap and water are more effective than hand sanitizers. And I actually have a couple of studies here, and I'll come up to them in a minute, okay? So we'll get to that. I know that's often on people's minds. I saw this here. These are the cavity wipes. These are really popular now in clinics and hospitals, and there's a few different formulations on them, right? And if you take a look, all these things usually have what the active ingredients are, right? So this one here, isopropanol, and then it has a few other things in there. The water obviously is not the active ingredient, but these here, other compounds of butethanol is also another alcohol. I'm not familiar with that one, but you know, this is the kind of thing where a company has gone and they've figured out a formulation that works. And if you take a look, apparently this works against TB, tuberculosis, MRSA, so Staphylococcus aureus, and some viruses there, HIV and hepatitis B virus, right? So they've formulated the last agent there is basically something called a surfactant, and I'll talk about that too. This is actually a pretty strong chemical. Okay, I'll get to the soaps in a minute, okay? Like I said, I want to compare them with hand sanitizers. I guess I kind of thought they were next, but I guess not. So there's lots of chemicals out there, okay? And kind of the key thing is to have something that's relatively reactive, and it's going to usually destroy membranes or proteins, right? So another big group of chemicals are halogen-based compounds. And so if you have an old first aid kit around your house, it used to be pretty common for them to have iodine in them. And iodine was kind of a disinfectant. You know, you got a wound and you clean it with some iodine, and that was kind of the whole part and parcel of it. If you've ever had gone camping and you get the, I can't think of what the name of them, those little tablets that are used to purify water. I don't know about the newer ones. Actually used some this summer. I never looked at the ingredients, but some of the older ones used to be iodine tablets, right? So iodine is a relatively reactive compound and will destroy proteins and whatnot. Probably the most common one is bleach. So bleach has chlorine in it. Chlorine is a halogen. And again, something that you don't have to use in the full concentration. You can dilute it. These things are reasonably persistent. They're, you know, in some ways similar to phenols in all their uses. Maybe not quite as nasty, and depending on what it is, could be more or less expensive, right? Iodine is a little bit more expensive than bleach, for example. Bleach is dirt cheap. Question?
Why is it iodine and chlorine are more common in using halogen chemicals than fluorine? Electronegativity.
Good question. Fluorine, if I had F2, that's extremely dangerous chemical. It's also not found in liquid, right? There could be a cost issue as well, right? I know that that bleach, right? I mean, it's so cheap, right? It's a very, very cheap chemical. You know, go buy a jug of bleach, right? It's like $3.99, right? I mean, it's super cheap. So, you know, some of those things come in. But fluorine is actually very, very reactive. Like if you had hydrofluoric acid, like don't touch that stuff, right? You know, hydrochloric acid, a lot of people know about it because it's, you know, in chemistry classes and whatnot. And the same thing, you don't want to touch it. But if I had to dilute a hydrochloric acid, I've splashed it on my hands many times. It's not a big deal. You wash your hands, you're fine. If you had hydrofluoric acid and I accidentally splashed even a dilute amount on my hands, I'd be more worried. Yeah, and just in terms of the reactivity. Okay, so I didn't want to linger too much longer on this one, other than to point out bleach, right? Bleach is pretty commonly used, again, for floors and things like that. And it's cheap. Another group I think I mentioned, or maybe I was mentioning this in one of my other classes, is peroxides, peroxygens. There's a few chemicals like this. You sort of see them again in first aid kits. I think we're kind of getting away from those in first aid kits because this stuff here actually expires pretty quickly. You may know that if you've ever done your hair and bleached your hair, hydrogen peroxide is kind of that active ingredient that bleaches your hair. But if the kit is kind of old, it's not going to work so well. So we're kind of getting away from those. But you can see that a lot of these are effective against endospores. So that's a use where if there are endospores suspected to be present, peroxides are used. Ozone is used in water treatment in many places. We don't use it here in town, but some water treatment plants use ozone, a very strong oxidizing agent and actually relatively dangerous gas as well. So places that use it, you know, they have to have all these special precautions for the water treatment. Okay, so up there at the top, let me just see. I think I see somebody has a question. Let's see what that says here. Somebody says, when I had surgery, they covered me in iodine before. Yeah, so it used to be common. I don't know why it's become less common. Like I said, to use iodine as a disinfectant. You know, trends come and go. Sometimes there's economic reasons. Sometimes there's actually good data or different alternatives or new technologies. You know, I mean, there's all these things kind of come and go, right? What doesn't come and go is soap. Okay, so this group here, detergents and soaps, fall under a group of chemicals that we call surfactants. So from a chemistry perspective, when I say surfactant, I mean something that has a hydrophobic and a hydrophilic component to it. If that means anything to you. I know different people have different comforts with chemistry, but what does that mean? It means it's sort of the compound sort of has a water-soluble part and sort of an oily part. And that's kind of how soaps work and detergents, right? Is that they the oily part of the compound can actually dissolve grease and things like that, and the water-soluble part can actually be attracted to water, and so it can help it to wash away. And so these things here aren't usually necessarily antibacterial or antiviral, although the soap will affect membranes and envelope viruses. But kind of the main thing you're doing when you're using a soap or a detergent is really just washing away the gunk. You could imagine, you know, my hands here, right? There's lots of little nooks and crannies. I've got little cracks around the fingernails. There's lots of places for things to hide, right? Depending on what I've been doing. You know, there could be dirt or grease or food particles or whatever, and all those places are opportunities for microorganisms to hide. And so, you know, who knows what I did in the last hour, right? Did I sneeze into my hand or whatnot? And this is why, you know, there's such an emphasis on hand washing, particularly with the pandemic, you know, where, I mean, you don't know what you just touched, right? On my way to lecture here, how many doorknobs and things like that I touched. You know, I'm over at the computer touching the keyboard. You know, who knows whose germs or whatever are around there, right? So this is why hand washing is really emphasized, and particularly in certain things like surgeries and whatnot, obviously it's essential. But like I said, most of it is just that de-germing, where you're actually just physically removing them, not necessarily killing. But that's good. That's a huge effective control mechanism. Of course, I've got a cartoon for you, far side, you know. Some people, you know, I try not to, when I go to a restaurant, pay attention to what other people are doing in the washroom. But I know some people are really sensitive about this issue, you know, people going to the washroom in a restaurant and not washing their hands. And so Gary Larson figures there should be an alarm. So tons of studies on these. This one I found a few years ago. It's really fascinating, and talking about a hand washing study on college students, so totally relevant to you. And they were looking at diversity of bacteria and also the sex of the college students. And here's some of the findings, right? So it was a small study, but 51 students, so that's 102 hands. And here's some of the results. So they found 4,742 species of bacteria. Wow. Just on a few people, right? That's amazing. Average hand, that's about 150 species. Left and hand, right, we're only 17% the same. Totally makes sense, right? I mean, I totally do different things with both my hands. You know, sometimes I'm working, I'm drinking my cup of coffee or tea with my left hand and, you know, using my computer mouse with my right. You know, think about all the other activities you do. You know, you brush your teeth, you know, sanitary things that you might do, et cetera, et cetera, et cetera. Right? Yeah, usually if you have a dominant hand, that thing is probably getting into a little bit more business than your non-dominant hand, right? Here's the other thing here. How come this is not clicking? Try this again. Maybe I need a new battery at some point here. Yeah, here's the other thing, right? You know, throw this one up here, and women's hands have the greater variety, and like, you know, you start seeing some of the female students, they're just like, yep, yep. Probably no surprise there, and actually there's quite a few reasons for this. You know, I know some people are thinking about just generally what they're doing at home in terms of chores. It's true. There's tons of studies on this to show that women probably do more than their fair share of household chores. And certain chores in particular, like washing the dishes, doing the laundry, women, and like I said, doesn't necessarily your house, but it definitely, that's the data shows that that's the case. And those things are going to contribute to different bacteria. If you have children, often there's an imbalance on who's changing the diapers. And the other thing about women as well, of course, women have their monthly cycles where you know, the body temperature and pH and things like that of the body actually change, just slightly, but it's enough to change the balance of the types of microorganisms that are found. So, like I said, interesting study. There's lots of them like that, and I think the bottom line is we have a lot of microorganisms on us. Washing our hands is probably a good thing. Here's one of the studies. Actually, I have two studies I want to show you that are comparing soap versus hand sanitizer, and just to show you kind of, you know, what do we think we should do, right? So this was a study done in, was it a daycare, I think? Yeah, it's a daycare. So you can see three groups. One group just, okay, we're not going to tell you anything. One group were told, you know, they installed extra hand sanitizer stations and told people, you know, how to do it, right? You know, there's some technique in terms of, you know, you're not just putting it on your hands and slapping it off, but you're trying to get around the nooks and crannies again, right? And going for a good, let's say 20 seconds or whatever is usually what they recommend. And same thing with hand washing, right? They showed people proper technique and et cetera, right? And this was the finding, is that in this case here, the hand sanitizer group actually did better, right? And that the hand sanitizer group actually less likely to be prescribed antibiotics and so on, okay? So one thing to say, this is one study, and two, this is really hard to actually control for. One of the things that the researchers admitted is that the hand sanitizer was in fact much more available than hand washing sinks. And so something they did, and I don't think they actually published the data on this, but just talking to the people, you know, people were excited about the hand sanitizer stations, and they were using them probably way more frequently than the hand washing people. So this is one study. Like I said, it's really hard to control for, right? You know, to really study these things. More studies are like this, that they're actually showing soap is better. And there's a couple of reasons for that. One is that hand sanitizer, often people are not rubbing it properly. I've seen so many cases where literally I see somebody get the hand sanitizer, a tiniest drop comes off and they're just like this, and then they walk away, right? So you need enough, and like I said, you need to have sort of proper technique. The other thing about hand sanitizers is alcohol is the active ingredient. And so alcohol is effective against certain things much more than others. So envelope viruses, for example, are susceptible to hand sanitizers. So that would include HIV that they had on that list, coronaviruses, influenza viruses, but that does not include norovirus. So we haven't really talked about norovirus too much. We're going to get to that eventually, but that causes severe vomiting and diarrhea. And probably everyone has had it at one point. It usually lasts about 24 hours, and it really sucks. And it's super, super infectious. Hand sanitizer does nothing, right? Question?
Should you be giving hand sanitizer to toddlers
I think as long as they're using it correctly. So she was asking if you should be giving hand sanitizer to babies or toddlers, right? And again, sometimes I don't know what the other ingredients are in them. I bought one from Walmart at the beginning of the pandemic, and I still have it because I don't use it because it stinks like crazy. I don't know what's in it, but whatever that is, it lingers on my hands forever. Because I know that I think like the first time I used it, I did it, and then I ate something and tasted it on my tongue. I don't know what the chemical is, so I'm just like, I just stopped using it. But yeah, it's a good question. The alcohol will evaporate very quickly. The other ingredients is the real question. Yeah, so read the ingredients. I don't know, I like reading ingredients on things. I like to see what's in products, chemical and otherwise. So this one here is showing that the washing was much better, the hand washing. So in some ways they complement each other, right? You can't have sinks everywhere. So having hand sanitizer, I see like they're all over the hallways here, and it's at least a quick fix, and it is effective against coronaviruses, which is good news. So I think I kind of said this already, right? Technique is important. The actual germ really counts, right? Like I said, hand sanitizer is not going to work on noroviruses, but it would work on influenza viruses and coronaviruses. And proper hand washing really is the gold standard. Okay. I think I mentioned like surgery, right? So again, if being in a surgery group, you know, they're going to teach you proper technique, and you watch the surgeons, they're on a clock, right? They have to wash and scrub for, I don't know what the time is, 2 minutes or something like that. And it has to be witnessed that they had done it properly. And this can get rid of like 99 point something % if it's done properly. And so hand washing is a good thing. It's all the stuff, right? All the stuff mom tells you, you know, wash your hands, right? Eat your vegetables. I've had this one here. Trying to remember where I got this one here. It was not my shot, but maybe it was a previous vaccine that I had before, and I snagged an extra one to show you that you know, these wipes are not always just alcohol based. This one is detergent based, and that's that chemical I showed you before, benzalkonium chloride. And this is a surfactant. And this is a very strong detergent. And so you can see it's being used in one of those little wipes that you clean someone's skin off before putting an injection, right? Okay, so a few more things, all having their uses. One that is not really used so often anymore are these heavy metals. There's a bunch of heavy metals out there. The two that I'm most familiar with are copper and silver. Mercury, of course, is toxic, but it used to be used as a disinfectant. Go figure, I guess, you know, we didn't know. They're showing here, what we have is some old, excuse me, old pennies. New pennies are not made out of copper, right? So old pennies are. And they basically did a bacterial lawn and plucked the pennies onto the lawn, and you can see that there's antibacterial killing where the pennies were. I'm starting to see with this pandemic advertisements for copper things. And this is because of the antimicrobial properties. So for example, I saw an advertisement for copper doorknobs, right? And that was actually the claim it was making. And that is actually a true claim, is that copper does have antibacterial properties. The other example here is a copper water jug, right? These are common in some parts of the world, and the water, it doesn't get stale, right? It's, you know, stays nice and fresh and sharp. And copper is not, if you drink and have small amounts of copper in water, it's not a big deal for a human. It really isn't. In fact, I've tested the water here at the college, and we have copper in it. Why is that? Probably copper pipes somewhere, and it's not a big deal. Higher concentrations, which is extremely rare, can make people a little nauseous, but smaller concentrations, you know, might add a tiny bit of discoloration or something like that, but not going to affect human health. Okay, so one of the other big groups of disinfectants are the aldehydes. Aldehydes is a certain type of chemical, and I won't get into chemistry on that, but again, something relatively reactive. And there's a whole bunch of these out there. The big one that people might have heard of is formaldehyde. Formaldehyde, it used to be used very commonly as a preservative for biological specimens and human embalming for funerals and things like that. We've kind of moved away from it because it's carcinogenic. But there's a whole bunch of other aldehydes out there that kind of fit the bill where they're relatively reactive. They will destroy proteins. And the other thing is a lot of them are super cheap. You can see I found this one on the internet, ortho aldehyde, OPA. That one is a relatively common one, and it comes in a bunch of different formulations. I used to have one in the lab that I think it was that one. I don't know why, but they added a little bit of pink coloring to it, right? And you could dilute it a huge amount, just like the phenolics, right? So I'd add like, maybe this much and then a bunch of water, and we all called it pink death, right? It was our disinfectant we used in the lab. And then eventually they changed the color to blue, so we changed our name to Blue Death, just for fun. But that's what it was, I believe. Like I said, there's a whole bunch of these out there, and they're also relatively cheap. And so this is often what you see. I don't actually haven't looked at this one here yet, but these disinfectant wipes here. I'm sure it says the active ingredient on there somewhere, but without my glasses, there's no way I'll read that. So maybe I'll check it after class. But there's a whole bunch out there like that. What was I going to say? I think I saw somebody might have a question there. Let's see. Oh, yes. Okay. Thank you to whoever put that that point there. There's a comment there about somebody working at a nursing home, and there was a silver wrap used for a wound. You can see I have silver on there. Silver used to be used a ton as an antiseptic. Silver nitrate in particular was a really common antiseptic. So if you've had a baby or know someone who's had a baby, you might know that one of the things they do when the baby is born is they put antibiotics in the eyes. And the main reason why that's done is actually gonorrhea. And even if you don't have gonorrhea, they still do it. It's pretty much universal because there are other potential bacterial infections that can cause eye issues. Gonorrhea in particular is quite serious because it can cause blindness in a baby, right? But other bacterial infections can be serious. So it's kind of a standard thing. They put antibiotic drops in the eyes. It used to be silver nitrate they would use. But silver, it's expensive, right? So this is just an economic thing, right? In fact, we have silver nitrate in the lab here. And I had I think it was a 500 gram container, so about this big. And the price went from $1,200 to $1,800. So we were told we can't buy that one anymore. I'm not sure what we were using it for. It was the other chemist was using it for something. But it's expensive, right? Whereas antibiotics, like honestly, we're talking about the types they're using. It's pennies, right? And for the amount of protection it can give and prevent any potential issues for the newborn, it's great. Just trying to remember, I believe I saw there's somebody with a science fair project about 3 years ago and was testing silver on something. I can't remember what he was doing now. But there are a number of products that are using copper and other heavy metals, and silver, of course, as well. Silver just being a little bit more expensive than copper. Okay, so last one. Okay, I know your brains are full of chemicals. Last one to consider are these gaseous compounds, and the main one is ethylene oxide. And this is really just to cover a use of something that is like, you can think about all the things I've mentioned. I've mentioned autoclaves being super important, okay? And you can autoclave all sorts of instruments and bed sheets and whatever, right? Things that can get wet or at least fit in the autoclave. A lot of these chemicals can be used for wiping down surfaces. So like I mentioned, it could be a floor, it could be a desk, there's all sorts of things that can get wiped down. It could be a payphone, I mean, who knows, right? So what about things that, we want to sterilize them, but, it's hard to get at, right? So class example is all sorts of instruments like heart and lung machines, right? You can't just have a heart and lung machine and then give it to a new patient and then infect the new patient. There's all sorts of laboratory equipment that they manufacture as well. There's inner parts and stuff. And so in certain labs as well, pipetters and instruments, you're not going to disassemble the whole thing. You can't put it in the autoclave. And so you can use these gaseous compounds. Like I said, ethylene oxide is kind of the most common one. Here's an ethylene oxide sterilizer, a small one. You can see it just basically the door opens and they put the instruments in, and it's going to have really good ventilation. This is a really toxic gas, by the way. But because it's a gas, it's not going to linger. They're going to, basically flush it with fresh air, sterile fresh air, and get rid of it. I saw on the internet some medical manufacturing company, and they had this massive warehouse, and the whole warehouse was a giant ethylene oxide chamber. I don't know what they're doing. I can't remember. That was a while ago now. But different manufacturers, like I said, have use for these things. They want to sterilize something. They want to guarantee it. They don't want to expose it to heat, and they don't want to disassemble it. And so this is what you can do. So the last category, which kind of leads into the next category, is sometimes antibiotics are put into things. Not really going to talk about them too much, but you see that sometimes certain formulations of things have antibiotics in them to deal with, and they're not really considered disinfectant, and they're regulated much differently because they are drugs, right? And so it's just worth it to mention them, that sometimes you see these things now that might have antibiotics in them. Okay, so want to just kind of shift gear for a few minutes and then wrap up the topic is, how do we know which ones are the best? Okay, and there's a few different methods for evaluating these things. Some are kind of standard methods. One method it goes by a few names. I think I got this term from the textbook, the in-use text. So this is just a field test, right? So you're trying to figure out, okay, which disinfectant works. Okay, well, I'll wipe down half this bench with product A and half this bench with product B, and then I'll swab it afterwards and see what I can find on a petri dish, and maybe we'll get answers, right? So this is not bad. It's kind of like a practical use of it. Problem is, people aren't necessarily going to be consistent in terms of, let's say their wiping technique or how much they've used and all those kind of things. But it is used in some scenarios. Like I said, trying to evaluate what is going to work. We can be a little bit more quantitative about this, and we can actually do something called a dilution test. So dilution test, you get these little rings or cylinders or whatever you want to call these things, and you basically stick it into a culture of bacteria. Pull it out, let it dry, and you're going to test different types of bacteria. So notice I have 3 different species here. All right, so there's good reason for this. If you take a look, E. coli, of course, is gram-negative, or Salmonella. E. coli, Salmonella are kind of similar in terms of their susceptibilities, and Staphylococcus is gram-positive. Okay, so you've sort of checked those boxes. You've got a gram-negative, and you've got a gram-positive, because generally gram-negatives tend to be a little bit more resilient. Again, it depends on the type of disinfectant and whatnot. Some are actually more effective against gram-negatives. But on a general trend, gram-positives die easier. So you just want to check, right? You got 2 different sets of biologies. And the third species I've mentioned a few times already, we're going to cover a bit more later on the course, is Pseudomonas Originosa. It is also a gram-negative. Now, Pseudomonas Originosa is kind of one of those freaks of nature that it just naturally is tough. It's naturally resistant to a bunch of disinfectants. It's naturally resistant to a bunch of antibiotics. It's a little bit of a nightmare, really, in some ways. And so what you're doing is testing kind of, a tougher organism to kill. So testing 3 organisms, and there's this dilution part. So in the dilution part, you can take the disinfectant and you can make dilutions of it, right? So, this could be Mr. Clean. How much do you use? Do I add 1 cup to 1 liter, 1 cup to 4 liters, all those kind of questions, right? So this is actually the test that determines, what that recommended concentration is going to be. And sometimes you see in the literature, people talk about the Phenol Coefficient, meaning they're comparing something to phenol. All right, I told you phenol is particularly nasty, and it's been around a long time. So sometimes I've read about that in the literature. but you don't need to know about the phenol coefficient. I think it's mentioned in the textbook. But really, this dilution test is just trying to find what the effective concentration is. And sometimes this is also called an MIC. This term MIC, minimal inhibitory concentration, is more commonly used with antibiotics, but it applies to disinfectants. And what it means is, what's the smallest concentration that will kill the organism? So you can see these test tubes here. There's some different concentrations. So we have 2 micrograms per mil, 4 micrograms per mil. The organism is fine in that concentration of disinfectant. At 8 micrograms per mil, that would be the minimal inhibitory concentration. That's where it is actually being killed. So this one here, you can do it in test tubes. You can do it in those little multi-well plates. I've done this a few times. Usually you do it in triplicate and all those kind of things just to make sure. And it's relatively effective and gives you an idea how strong something is compared to something else. I guess I forgot to mention, you make the dilutions, you put the bacterial rings in, and then the bacteria go back into media to see if they grow after being exposed to disinfectant. But really, it's just, does the disinfectant work at this concentration? So one more test can be used. Oh, come on, what's going on with my mouse here? So one more I want to show you, and again, this is something I've seen about 100 times at science fair, is these disc diffusion tests. So disc diffusion test is very easy to do. You get these little filter discs. You can put the filter disc into the disinfectant. So let's say Mr. Clean or Listerine or something like that. And then you put that on a lawn of bacteria. So the lawn of bacteria is just the bacterial of the plate. And then you can look for what is called a zone of inhibition. So the bigger the zone of death around the disc, the more effective is the disinfectant. So like I said, I've seen this a bunch of times at science fairs. There's always some kid that wants to test something, whether it's a new product or a couple of times I saw these kids, they wanted to test household spices, right? So something like garlic has antibacterial properties, right? So, they test garlic versus, nutmeg and whatever, right? And it's very, the thing I like about this particular test is it's very visual. You can see here we have Staphylococcus, E. coli, and Pseudomonas. You can see Staphylococcus, everything is killing it, right? E. coli, this one compound, hexachlorophenine, does not seem to be affecting E. coli at all. And Pseudomonas is pretty happy with 3 out of the 4 disinfectants, right? So like I said, you have this nice visual, and you can see that, we've got a more and more resilient organism as we go to the right. And you can see that this one compound here, this chlorine, for example, is the most effective. So that might be the one to use in whatever scenario that you're looking at. So we'll come back to these tests. They're kind of basically the same things that might be used for antibiotics, right? So when we're evaluating antibiotics. All right, so just see a question here. Right, yeah. Somebody's just saying that they did this in high school or something like that. It's a pretty, like I said, it's a pretty common test, very easy to do. Doesn't always work out. I mean, that's kind of the caveat, and that's kind of true with any scientific test that's done if you're inexperienced and have not done it before, right? Usually in high school or even in university, you do a lab, and it doesn't always work the first time, and that's kind of the nature of the beast. But it can work really, really well. Okay, so I mentioned that I'd show you kind of a sample midterm type question. You're going to have a midterm type question that is going to give you some sort of scenario. And so, for example, this one here, I think I've mentioned it before. Here's a scenario: somebody vomits on the floor. What do you do, right? So you don't need to know all of the disinfectants, but in this case, it's asking you to talk about 3 of them. Okay, so when you're doing your studying, pick on some that you think might be the most useful. Learn 3 or 4 of them, and hopefully that will get you through the test. Scenarios could include all sorts of things. I think in the past I've had a scenario. So by the way, I've had people say autoclave it. You're not going to autoclave the waiting room. There's people in there. You can't fit the waiting room in the autoclave, right? But some of the other scenarios I have had, our autoclave is perfectly legitimate, right? For example, how do we sterilize let's say, some instruments such as scissors and forceps used for surgery. All right, so autoclave would be the right answer in that case. Mr. Clean would probably not be the right answer there, right? So this is what I want you to do is make the connection. I think last year, if I'm trying to remember, the scenario I had was a patient was infected with Staphylococcus and had been discharged from the hospital, and you are asked to disinfect the room, give some methods on what you might use. So this might be similar to the waiting room, right? In terms of we're concerned about Staphylococcus being on surfaces in the room, right? So you'll have to think about that. I'm not telling you what the scenario is, but you'll find out when the midterm comes. Question?
Yeah, do you want to see the name of the thing or like the store name?
The more information you get, the better.
Okay.
Okay. Yeah, it kind of depends on the compound. And you can see in this particular question is asking you to explain a little bit about how it works. Sometimes I mean, depending on the question, I think I'm trying to remember, it was last year, the year before, I didn't ask that part, but I asked to be a good description of how it is going to be used by the user, right? Because that's also important. If you think about, like I just said, you know, you're sterilizing, let's say, some scissors, okay? You can use disinfectants, but you're not going to wipe them off, right? You're probably actually going to soak them because that's going to get all the surfaces on it, right? And then you're probably going to have to wash them off because you don't want to be like dealing with somebody and getting like the chemicals on the person, right? If it was alcohol, then that's not a big deal because it actually will evaporate, right? Not going to be the most ideal use. I mean, you could boil scissors as well. You could, you know, I mean, that's going to work except for maybe some endospores if you don't boil long enough. But, you know, like I said, you know, some answers are going to be more right than others, and that will be part of your grade, right? Yeah. Okay, so I think I have a Kahoot here. Yes, I do. Okay, so load up your apps, and I got a few questions here about disinfectants and microbial control. All right, I think this one is 8 questions. Okay, here we go. Question 1, what is sterilization? It's not a tough one. It's killing all microbes, right? Not just bacteria, but also killing viruses and protists and whatnot. Okay? So I think looks like more people than not got the right answer, but it's a tough one. Okay, all of the following are antiseptics except. Okay, so I guess I forgot to talk about what an antiseptic is. So let's talk about that now. Just gonna let the time go out. I did mention at the beginning, it's somewhere in the notes. I know that. Antiseptic means something that you're going to use on the surface of somebody's skin usually. It doesn't have to be that, but that's like the scenario 99% of the time. Okay, so you can see the other answers. So bleach is the correct answer. Okay, so what were the other answers? Hydrogen peroxide, alcohol and iodine, all those other things are safe for skin. Bleach, I mean, it's okay, but I mean, concentrated bleach is going to, you know, cause a reaction with skin. You know, it's not going to be as nasty as some other chemicals, but you're not going to be wiping down someone's skin with bleach. You're not going to have that part of your first aid kit, right? Medical manufacturers use this method. Correct answer, ethylene oxide gas. Autoclave, they're not usually doing that at the manufacturing end necessarily, because you know, things get wet and all that, and it's just not as practical for the manufacturing aspect of things. So medical manufacturers, they're often sterilizing things by either ethylene oxide gas or UV, and then they're packaged up in some sort of sterile package, and you're going to receive it like that. Autoclaving is going to make things wet. Drying out things and all that is just going to take a little bit of extra time. There might be some exceptions. Some liquids might be autoclaved that are made by medical manufacturers, but usually the common ones are UV and ethylene oxide. Okay, correct answer is false. Envelope viruses are kind of the wimpiest of all of the things on the list of microorganisms. That envelope makes them a little extra sensitive to chemicals. It tends to be quite fragile. There are quite a few envelope viruses out there that can barely survive outside of the human body. Most of them, it's like maximum 24 hours. HIV is a good classical one that really cannot survive outside of human bodily fluids. The exceptions are some respiratory viruses. Coronaviruses and influenza viruses are extremely sensitive, but you've got to realize with respiratory viruses, often there's things like mucus that accompany them and allows them to survive a little bit longer outside in the environment. But envelope viruses are really wimpy. Another footnote too. That's actually why influenza travels and is spread a little bit better in cool temperatures, right? There's sort of an optimal humidity for that virus to survive, which is why it tends to be a bit more common in temperate climates, not really usually an issue in warmer places like, let's say, Mexico or whatever, right? Just sort of that, there's a certain optimal dryness and, like I said, relatively sensitive organism. Okay, so good job, folks. 5. Dry heat sterilization is used for all right, good job. Things can't get wet. True or false? Ionizing radiation is high energy and non-ionization radiation is low energy. Another good one. Well done. Okay, 2 more questions. I've raised it from up there. True or false? Phenol and Phenolics are used to elaborate. False. Okay. These are useful for the opposite reason. They're persistent, right? Which is why they're found in some of these cleaning products, and you know, and psychologically too, right? You know, you walk into a house and you can smell that Mr. Clean, and you're like, oh, it's got to be clean in here, right? You know. That's another thing that's nice about them. Surfactant refers to alcohols and ethanols. All right, false. Precious, well done. Joanna, Silver, and Morgan. Okay, so try to make a food for every unit. Whether I share with them in class or not, I have put the links up on Moodle. I think there's a way to go in and practice yourself. Some of them are better than others. That one there, I'll confess, I found a Kahoot on there and sort of edited a little bit and realizing just now that some of the questions were not quite what I wanted them to be. Been trying to just introduce some classes in appropriate times to break things up. Sometimes I'm just behind, so I skip them. So I apologize for that. I know they're lots of fun. Everyone wants to play games. Okay, so switching gears to topic 10. So topic 10 is the last one that's going to get covered on the exam. And I'm going to talk about the exam on Tuesday. I don't know if we'll quite finish topic 10 on Tuesday. My plan was to finish topic 10 on Tuesday to give you a week to get the material in there. But we'll see where we're at, and I will reserve some time on next Tuesday to talk about the midterm. Okay? So topic 10, unfortunately, is a little bit like topic 9 in that it's kind of, in some ways, a big, long list. I think it's more interesting. I love antibiotics. I think they're super fascinating, and it was part of my research in antibiotics. So a topic that's near and dear to me. And so let's talk about these things, okay? First, a history, okay? I didn't write this. This is just kind of a little joke, but I'll show you. It's kind of cute. So a history of antibiotics. 2000 BC, here, eat this root. 1000 AD, that root is heathen, say a prayer. 1850 AD, the prayer is superstition, here, drink this potion. In 1920, that potion is snake oil, here, swallow this pill. 1945 AD, that pill is ineffective, here, let's use penicillin. 1955, oh, things have mutated, here, take tetracycline. 1960, 1999, oops. Here, try this more powerful antibiotic. All right. Year 2000, the bugs have won. Here, eat this root. So there's a lot in there. If you know a little bit with history of science, little things and tidbits in there. And so we're going to talk a little bit about this as well. Probably not get to it today, but things like resistance and mutations and whatnot are kind of important. This whole story of antibiotics. So some quick. I think I got. So some quick definitions for you. Okay, I know you take a pharmacology class in your second year, and pharmacology just really means how drugs work in the body and otherwise, right? And there's a lot to discuss about pharmacology in terms of really there's thousands of things you can think about in terms of how the drug is getting into your body. Is it injected? Is it ingested? How long it's going to persist, right? Some things you have to take 2 pills a day. Some things it's 4. There's lots of things like that to consider. So this is just kind of just a little touch of pharmacology just for one lecture, I guess, in some ways. Another definition is chemotherapeutic agent, right? And everyone, when they hear chemotherapy, they think cancer. But that's just one application of chemotherapeutic agent, right? It could be a drug that works against something else. So I went to a conference. It was actually called Antibiotics and Chemotherapeutic Agents, and it was all antibiotics. The whole thing. Nobody was talking about cancer at all, right? So it just means drugs, really. Antibiotic means a drug that kills a pathogen. But 99% of the time when we say antibiotic, we actually mean an antibacterial drug, right? There are antiviral drugs, there are antifungal drugs, and so on. So I'm going to try to be clear to use that language, and I'm going to say antibacterial versus antiviral. Okay. If I do slip and say antibiotic, I probably mean an antibacterial drug. Doesn't have to mean an antibacterial drug, but that's kind of just what everyone uses it for. Okay, so there's some terminology for you. Not too much today. Oops. So little history. Just want to talk about history of antibiotics for 5 minutes, maybe 10 minutes, and there's some points to make. First is, 100 and whatever years ago, we did not have antibiotics. We had a smallpox vaccine, and a lot of kids were dying. And this is the stat I found here. Apparently, a third of children died before age 5 due to infectious disease. And what would you do? We were very good at treating symptoms, but not treating the cause, right? The infection. And so if your immune system could handle it or whatever, you were good. If not, it could be a death sentence for certain infections. And if you take a look at the last 100-ish years, we've made a lot of progress, and for a lot of different reasons. And the one thing that's not put up here, by the way, one of the biggest inventions that has improved the health of humans, flush toilet, right? Think about it. Having a way for us to get rid of our waste in a safe and sanitary manner, that's huge. You can see sanitation is put up there in public health departments and things like that, made a huge difference. You can see right there in the middle, penicillin about 1945. That it was a huge advent in treating infectious disease. Before that, we could do prevention. Now we can actually hit the other end of that is what happens if and when you do get sick. Now we can actually treat a lot of people. So, and you can see these stats as well, right? The 10 leading killers, 1900 versus 2000, 100 years difference, right? You take a look at 1900, the top 3 are all infectious diseases. And in fact, some of these things here, diphtheria, probably nobody here has ever known anyone with diphtheria. It's kind of just gone, partly due to vaccination. My great-grandmother died of diphtheria, and that's where I know it from, but I don't know anybody else closer to me. I never met her. Now you can see that the profile has changed, right? We're living longer, and so we have diseases such as cancer and heart disease and strokes being kind of some of the main killers of humans. You can see there's some new ones on there. HIV has made the top 10 list. That wasn't a thing in 1900 and so on. So, the profile changes, but a lot of it due to us just living longer, and we're not dealing with these other things quite as much. So let's talk a little bit about drugs and a little bit of the history of drugs. This is going back, early 1900s, okay? We have this germ theory idea. And as humans as well, we're getting a lot better at chemistry. And so enter this guy here, and he had this idea. He called it the magic bullet, right? He's thinking, what if I could find a chemical that was like a magic bullet that would selectively kill the pathogen and not the human, right? So what does he do? He starts just going through chemicals and testing them on pathogens. And this is one of the ones that he found. I don't know where he got it from. I don't know his whole story. But this is apparently the 606th chemical he tested. And he found out that it actually had antibacterial properties. It killed the organism that causes syphilis. So early 1900s, this was a big deal. There was no treatment for syphilis. You may know in all these historical movies, all the European gentlemen are wearing those wigs. I guess that's how they got popularized, because a lot of people had syphilis, and it eventually causes balding, right? And then they become a fashion statement too, although not anymore, thankfully. They're really weird, those wigs. But anyway, yeah, so there's Salvarsan. It was something that required lots of treatments. And here's a treatment kit. And so my understanding is the way it worked was that you would go and visit a doctor, and the doctor would wash the affected areas, so the genitals, with the Salvarsan. You'd go in for several treatments. And it was making a lot of clinics very wealthy because before, no cure, now there's a cure, right? Like I said, big deal. So this is great. It wasn't the most effective antibacterial agent, but it was a cure. Whereas before there was no such thing as a cure to an infectious disease. So this is great. So people are starting to think about this now, right? They're starting to think about, okay, we know that certain pathogens cause certain diseases, and we can find chemicals that can maybe kill them, right? So another one was that had popped up in 1935 was Prontocill. This is the chemical here. It's called a sulfonamide. And we'll talk about how those work next day. But this one here could actually treat other infections, right? So streptococcal infections. And so it could be treated by injection. It's actually still used today in some contexts, is my understanding, although I've personally not seen it being prescribed. But apparently it's still used sometimes today. Like I said, we have better alternatives here. So not a lot of things out there, but there were a few things, and this got people thinking about, hey, maybe we could find others. Like I said, these weren't amazingly effective, but now it's on people's minds, and scientists and physicians and other healthcare people are thinking about this, that we can do this. We can actually treat infectious disease. This is great. So maybe the most famous person is Alexander Fleming. I could give an entire lecture on this guy, really fascinating story, but a couple of things to say. He was a doctor, he was Scottish, he was working in London, and he was treating patients for syphilis using salvarsan and making a good buck off of it. And he dabbled on the side, right? He had a little lab and, grew some microorganisms. And anyway, one week he was growing up some staphylococcus. And kind of what a lot of researchers do is you can put your thing in the incubator overnight, or if it's a Friday, like you don't want to come in on the Saturday. And he had a cottage or something he wanted to go to, so you just leave them on the bench top. Came back on Monday, and his experiment had an infection, a mold infection. And so this is not his picture, but probably looks something like this. So if you take a look, you can see the plate. You've got staphylococcus growth, and you've got some mold on there. And all around the mold is a zone of inhibition. So usually what happens when you have this go to your experiment, you're just like, oh man, and you throw it out, right? But he's like, wait a second, like something's killing bacteria. This is a good thing. Let's look at that. We know now that what he had was penicillium, and he figured out, like, he knew it was a mold, and this is what it looks like. It's actually a very beautiful looking mold. And that's where the name penicillin ultimately is going to come from. And so he started growing up the mold and making mold juice, right? Is basically what he was doing. And he started testing this mold juice on a whole bunch of things. So he had some cultures. He tested it. It worked against staphylococcus. It worked against streptococcus. It worked against gonococcus and so on. And didn't work against E. coli. Didn't work against salmonella. Did not work against tuberculosis. I don't know why he did not test syphilis. Maybe that they weren't growing it in the lab at the time, or maybe it wasn't culturable at the time. I'm not sure. That's my biggest question. Is that was his lifeblood? Why wasn't he thinking about that one? So this is amazing, right? Like, look at all these pathogens. He started testing it on animals. Right, you can see he has an experiment here. He tested on an animal, on a rabbit and a mouse, and they were fine. And then he even tested on a couple of patients. I think he tested on 2 patients. One person had an eye infection, and he washed their eye with the mold juice, and the other person was some sort of amputee, and they had an infection on their surgery, and it worked, like miraculously. He was not a chemist. He was not able to extract the chemical. But he figured there was a chemical in there, and he called it penicillin. The one problem with penicillin is it's spoiled really quickly. So you put in you make this mold juice, and it seemed to be effective for 2 days, kind of like max, right? And so that was kind of discouraging. And he kind of was like, well, yeah, cool, antibacterial stuff. He discovered an enzyme in his nose that had antibacterial properties, and he went on and just investigated other things. So it's kind of like a shame, he left penicillin on the wayside. But it turns out he published, and a lot of people were like, wow, this is pretty cool. Can I have some of that mold? He's like, yeah, no problem. So he would share the mold with people, and there were people that studied it for a while. So this is 1928, and so people were studying it for quite a number of years, kind of wondering what was going on. So kind of a cool story. Like I said, there's a lot of luck he had there. A luck that the mold, like he left his plates at room temperature. Mold grows better at room temperature. Not all molds have penicillin that have got infected by the right kind of mold and so on. But like I said, a lot of luck here. So he was sharing his mold with people. And one of them was this guy here. Ernest Chain was working in Florey's lab, and he read the paper and was like, hey, let's get a hold of that. Maybe we can, they're chemists, maybe we can extract it and study it a bit more. So they did. They extracted it. They were able to make it into a powder, and the powdered form doesn't spoil as quickly, right? It's a lot more stable. It's actually the solution form that spoils. And they did some experiments. So here's the experiment they did. They took some mice and they injected streptococci into the mice. Mice died, right? So for mice, they did a second batch where it was the streptococci and penicillin, and the mice were fine. So we're talking about 100% of the mice died, 100% of the mice survived. So a little bit of experimentation here, right? And they started getting doctors to test it on patients. Now, they were testing it on children. Now, some people are thinking there's some ethical issues with this. Yes, this is early, like there was not really a pharmaceutical industry back then. There were not standards of testing and care. They tested it on children because it was hard to make this stuff. And children were smaller patients. And a smaller body meaning you had to use less. It was very expensive to make initially. And they knew that there was a huge use for this. Just take a look at the year. What's going on at this time? Yeah, this is World War II. If you look back at the numbers in terms of people dying in World War I, more people died of infections of wounds than the gunshot wound itself, right? And so they knew that this could be huge in the war effort. And so a whole bunch of things happened, right? And again, some really fascinating stories behind this, but these guys were in the UK, and you probably know that the UK was getting bombed, and so they didn't want to make a giant factory. So literally, they actually hired people to grow mold in their basement. Isn't that kind of funny? You want to grow mold in your basement? Okay, yeah, sure, sign me up, right? And they were doing this to help their country. And anyway, it's kind of, like I said, huge, interesting story. And there's some women there. They made some special flasks. You can see they can stack up so you can put more in your basement, I guess, was the whole idea. You can see that eventually they were working with the Americans to more manufacture this in larger numbers. And you can see there's a poster there from World War II era. It says, thanks to penicillin, he will come home, right? Did not take long before people realized that penicillin could cure a whole bunch of things. So check this one out. We had no cure for gonorrhea. Now we do, right? Huge number of things were suddenly treatable by penicillin. It was a miracle drug. In fact, they were starting to stick it in everything. It got a little bit out of control at one point. It was in like cough drops and like chewing gum, I think, or somebody trying to sell penicillin chewing gum. It just became kind of the wonder drug, and it really was a wonder drug. Like I think about all of the things that could kill you, and now, just give you some penicillin. This is kind of awesome. So I wanted to, so that's kind of it about the history, but there's some points that I want to make about this, right? One is that this whole idea of something we're going to talk about, I don't know if I'm getting to today, but something called selective toxicity. And this is the idea, is that you have a chemical that is going to kill the pathogen and not the host. And hopefully no side effects as well, right? And that's actually the case with penicillin, is that the side effects tend to be relatively minimal compared to a lot of drugs. Okay, so we'll get into that in a little bit about what, some of the effects of penicillin are. But this led to all sorts of people. This led to really, in some ways, the birth of the pharmaceutical era, where companies were starting to invest money in research and trying to look for things that can help people. And so penicillin was manufactured, and people are like, can we find other drugs made by mold and whatnot? So what do? You just dig up dirt, and you put a little bit of dirt on a petri dish, and you spread it out, and there you go. You get a whole bunch of different molds and bacteria and whatnot. And then what you do is you put a layer of I don't know, Staphylococcus or something on there, and you look for those zones of inhibition. So here's a picture of one. And so now if you take a look at this, look at all those zones of inhibition. That means each of those microorganisms are killing whatever it is you put on there, Staphylococcus. And so they are worth investigation. So this was done for decades, and we came up with hundreds of new drugs in a very short amount of time. So it's pretty cool, and they're still doing this today, believe it or not. And so, you know, this is worth, and I'll come back to this concept in a bit here. So if you take a look at this, there's a whole bunch of different drugs. Streptomyces species, these are soil organisms, they're bacteria. They're kind of weird in that they're filamentous and almost fungi-like. And for whatever reason, they seem to be, at least historically, a good source of a whole bunch of different drugs. You might recognize some of these drugs. I'm going to kind of give you a list of ones to know for this class. There's really too many to know, hundreds of them. And new ones all the time. So this was whole beginning of the era. Many of these drugs are natural, so they're found in natural sources like penicillin. Some are synthetic or semi-synthetic. So what do I mean by synthetic? Synthetic means entirely made by a chemist. Semi-synthetic means sort of a hybrid of that. Maybe you have a natural drug and you add a couple of atoms on one end, and suddenly it's a little bit more potent, or suddenly it has less side effects. And this is a pretty common thing done in the pharmaceutical industry with all sorts of drugs. You know, you have a first-generation drug, let's say it's an antihistamine or something, makes you really drowsy. And so they're like, okay, what can we do with this? And sometimes it's just a little experimentation, and they remove a functional group, and suddenly it has less side effects. Sometimes it's the opposite, right? So this is part of how that works. So a whole bunch of different classes of drugs. We're going to talk about some of these classes of drugs next day. And most of this we're talking about 1950s, 1960s. And we still refer to this as the golden age of antibiotic discovery, because most of the things that are in use today were actually discovered back then still. There was a bit of a gap in terms of the research done because we had suddenly so many drugs. Why research new ones? Unfortunately, due to things like resistance and whatnot, we're kind of at the point where we have to figure out what we're going to do about this. We need some new options. So up until about the 2000s, there was not actually a lot of research that actually was relatively minimal. So I'm going to finish on this slide. Like I said, the thing I want to emphasize is this idea of selective toxicity. Okay, so selective toxicity really just means you're targeting something that is going to kill the bacteria or the virus, but not the human. So in the case of penicillin, penicillin is actually targeting peptidoglycan biosynthesis. So it's targeting the cell wall of bacteria. And that's perfect because humans, our cells do not have cell walls. We do not have peptidoglycan. So we're trying to hit the bacteria where they're vulnerable. And so this has implications in terms of the drugs that we have out there. So you can see this slide here. It says we have the most drugs for bacterial infections. There are hundreds and hundreds of antibiotics. What about antivirals? There's maybe, I don't think there are 10 classes of antiviral drugs. I don't think there are that many. There are more than 10 antiviral drugs, but in terms of classes of antiviral drugs, there's maybe 6 or 8. So what is going on there? So think about how a virus works. A virus works by injecting its genetic material into a host cell and using the host enzymes and the host machinery to make new viruses. So viruses don't have a lot of things that are different from us, right? You know, they might have a viral protein, or they might have, a viral, let's say, RNA polymerase, and these are the things that we're targeting. Whereas a bacterial cell is much, much more foreign. In between, you can see fungi and protists. They're eukaryotes like us, so they have less potential targets for drugs. So the biggest class of antibiotics that we're going to talk about are, in fact, antibacterial drugs. And so we're going to spend the most amount of time on that next day. So that's where I'm done for today. And so thanks for coming. I'll see you on next week. Okay?